So in this video we are going to talk about the questions which appeared in stat and thermal physics in GATE 2003 examination. Okay, so let's continue with the first question. The statement is, the piston containing an ideal gas is originally in state X. Okay, see the attached figure here. So the gas is taken through a thermal cycle, that is from X to Y. That's the first process. Let me label this as process 1, X to Y, and then Y to X. Okay, so let's label this process as process 2. Okay, the work done by the gas is positive if the direction of the thermal cycle is okay. So in principle what we can do is we can resolve this process into two different processes, and let's see how we can predict the whether the work done in this cycle is positive or negative. Okay, so here I will draw two different diagrams here, PV diagrams, one depicting the process 1 and another one depicting the process 2. This P versus B. Okay, P versus V diagram. Okay, so let's fix the point X and Y. These are the two equilibrium states. Okay, the second diagram also. Okay, so here the first figure, it represents the process 1. Okay, this is process 1, and the second figure, it represents the process 2. Okay, so in first case, let's note W1 as the work done during process 1. So the work done, it is basically work that is equal to, because it's then during the process 1, it's the expansion. So work is done by the gas. Basically it's an extension in a sense that process moves, or the state moves from X to Y, and volume changing from V1 to V2, where V2 is larger than V2. So that it is an expansion basically. Okay, so work done during this process, work done by the process is taken as positive, so that is equal to P dB, and then its integration from V1 to V2. Okay, and this is a positive quantity. So W1, it is a positive quantity, and this is this PdV, it's given by the shaded area here shown in this diagram. Okay, so W1, it is positive. Okay, now let's try to understand that when the process moves from state point Y to point X again by following this path. Okay, so in this case the volume of the the system, it reduces from V2 to V1. So we called this as B2, and we call this volume as B1, where V1 is smaller than B2. Okay, so the work done during this process, it is given by this shaded area. Okay, so W2, again it is PdV, but now from B2 as initial volume and B1 as final volume, and this is going to be a negative quantity. Okay, and the W2 here, that is negative. And if you just take a look at the area under these two processes, that is process 1 and process 2, we notice that the work done in process 1, it's larger in magnitude as compared to work done in process process 2. Okay, so when we will add these two numbers, so that will give us the total area. Okay, and so not the total area, but total work done during this cyclic process. And after adding these two numbers, we will be left with only this area, the area which is bounded by this process. Okay, so this is the hatched area that will give us the work done. So net work done will be sum of W1 and sum W2, where W1 is, it is W1 is greater than W2, and further W2 is negative. Okay, it's negative quantity. So the net outcome is that the net work done, that is going to be a positive quantity. So therefore when this cycle is traversed in a clockwise direction, so then we will obtain a positive work done during this cyclic process. So therefore option A is the correct one here. Now let's continue with the second problem. So here it's related to basically the phase transition. Okay, a second order phase transition is one in which, so we have to pick any one of the statement, the correct one out of these given statements. Okay, so here what I'm going to do is I'm going to provide a summary of the different various kinds of first order and second order transition, and on what basis we decide that whether it's a first order transition or it's a second order transition. So let's try to understand this point in detail. Okay, so for the first order phase transition, so in first order phase transition, so the first point that we should note that it involves latent heat. It involves latent heat. Okay, latent heat L. So that means any process which can be described by the Clausius-Clapeyron equation, that's going to be a first order transition. What is the Clausius-Clapeyron equation? That is dP by dt. Okay, that is equal to L divided by T multiply by V2 minus V1. So where V2 and V1, they are the specific volume. Okay, so and the second point in in first order transition, that Gibbs free energy is continuous in first order transition. So Gibbs free energy is continuous. So that's the second point we should note. Okay, and the third point is the first order derivative of G with respect to T and P, that's with respect to temperature and pressure, are continuous. Okay, so what does this first order derivative of G with respect to T and P represents? So let's see, it's the entropy, that is equal to minus dG by dt. Okay, so that means in a first order transition, even the entropy, it's a continuous function, or from here we can define the entropy per particle as S divided by total number of particles. So that will give you the entropy per particle. It's continuous again. Okay, that is minus dG by N upon dt. Okay, where G by N, that defines the chemical potential. Okay, so at constant pressure. Okay, so that is equal to minus d mu by dt. So that what you can say is that even the chemical potential, that's continuous in a the first order transition, because it's ultimately it's connected with the Gibbs free energy per particle, which defines the chemical potential. Okay, because S, it's continuous, so that's how d mu by dt, the variation of mu with t, that's also going to be continuous. Okay, now what does the other first order derivative of G with respect to P represents? It's the volume. Okay, so volume, that is equal to dG upon dP. Okay, at constant temperature. Okay, this is also continuous, and from here, as we defined above, the entropy per particle, we can define the volume per particle. Okay, so that is equal to d G by N dP. Okay, at constant temperature, and that is equal to nothing but d mu by dP at constant temperature. So this is also continuous. Okay, these are continuous, both of these two quantities. Okay, continuous at phase transition. Okay, so now the fourth point is the heat capacity, that's Cx, that is T ds by dt. Okay, which is equal to minus, no, I think I made a mistake here while defining the first order transition. The first order transition. So first order transition basically they defines where the first order derivative of G with T and P, they are going to be discontinuous. They are not going to be continuous. Where Gibbs free energy, it's going to be continuous. I'm really sorry. Please note this correction. So in first order transition, the derivative of G with respect to T and with respect to P, they are going to be discontinuous, and further the higher order derivative may also be discontinuous, but it's the lowest order derivative which is going to determine the order of the transition. So therefore, in first order transition, the first order derivative they are going to be discontinuous first, and the second order may or may not be discontinuous. Okay, so it's the lowest order derivative which determine the order of a transition. So here the heat capacity, for instance, it's a that's T ds by dt, and if we replace s with dg by dt, so it becomes second order derivative of g to d2 g upon dt square. Okay, so this is going to be discontinuous. Okay, because dt that's equal to 0, so cx exhibit sharp spike. Okay, so here instead of writing continuous, yes, this is okay. First order derivative g with respect to t and p are discontinuous, not continuous but discontinuous. Okay, now regarding the second order transition, so in second order transition, okay, so g s that is equal to minus dg by dt, and also b that is equal to dg upon dp, all these will be continuous. Okay, these will be continuous, whereas the second order derivative of g, okay, second order derivative of g, they are discontinuous, okay. So the second order derivative of g, so for instance the cp, that's also second order derivative of g, t ds by dt at constant pressure, that is equal to minus t d2 g upon dt square. Okay, it's discontinuous. Okay, and the other quantities which are discontinuous, they are the isobaric expansivity, which is 1 by b dv by dt at constant, and then isobaric at constant pressure. Okay, and that's nothing but 1 by b d2 g upon dt dp. Okay, so it also involves the second order derivative, so this is also going to be discontinuous. Similarly, we can say that the kappa T, that's isothermal compressibility, so that is minus 1 by b dv by dp at constant temperature, and this is again the second order derivative of g with respect to p. Okay, this is also discontinuous in the second order transition. Okay, so therefore so from here we conclude that, from this entire discussion we conclude that out of these options, the plot of specific heat as a function of temperature shows a discontinuity. So because this validates this point that we just discussed in the second order transition. Okay, this is going to be discontinuous because so this is of the correct option. But what the first one, the plot of entropy as a function of temperature shows a discontinuity. Entropy as a function of entropy is because it's a first order derivative, so therefore in a second order derivative entropy, it's going to be continuous. See here, it's going to be continuous, it's not going to be discontinuous. Okay, the volume also, volume is the first order derivative of g, okay, of with respect to p, so therefore it's also continuous here. So therefore this is wrong for the second order case. The plot of comprehensibility, not comprehensibility, well, this will be compressibility, not the compressibility. As a function of temperature is continuous. Okay, no, it's not continuous. In the second order transition, this is going to be discontinuous, as I just discussed here. It's the expansivity and this is compressibility. So d point is related to alpha p. Okay, so this is also wrong here. Okay, so please pay attention to the point, because unintentionally I mentioned it to be a continuous here. That this point I'm talking about, first order derivative of g with respect to t and p in first order transition, they are going to be discontinuous. Okay, please note it. Okay. So let's continue with next problem. The statement is, consider the Fermi Dirac distribution function Fe at room temperature, that is at 300 Kelvin, where E refers to the energy. If EF is the Fermi energy, which of the following is true? Okay, so we have to make a right choice among the following given 4 options. So before we arrive at one of these options, so let's try to figure out the basic properties of the Fermi Dirac probability distribution function. Okay, so this Fermi Dirac probability distribution function is given by f of E, that is equal to 1 divided by 1 plus exponential E minus EF upon kVt. Okay, so that's the Fermi Dirac probability distribution function. Okay, so now I'm going to make a plot for this function under two different conditions. One at absolute zero, sorry, this is a straight line. Okay, so let y-axis it represents the f of E, and along the x-axis we are having energy. Okay, so now let me draw it first, and then I will come to the explanation immediately. Okay, so this transition point corresponds to E is equal to EF, and this curve corresponds to T is equal to 0 Kelvin. So let's first try to understand the property of this equation 1 at absolute 0. Okay, so at T is equal to 0 Kelvin, so let's imagine a situation where energy is smaller than EF. Okay, so that means we are talking about the all energy value in this direction, E smaller than EF. Okay, this corresponds to E is equal to EF. Okay, so we will come to E is equal to EF at a later stage. First let's try to understand the behavior below the Fermi energy. Okay, so for E less than EF, E minus EF is less than 0. Okay, so this means exponential E minus EF upon kVt, where kV is the Boltzmann constant. Okay, so this is equal to 1 upon exponential EF minus E upon kVt, and that is equal to 0. Okay, so if that is equal to 0, so that means, so in equation 1, so therefore equation 1 reduces to, that's a Fermi Dirac probability distribution function that can be approximated as 1 upon 1 plus 0. Okay, so why this is approaching 0? Because when we will put here t is equal to 0, so this will become the exponent will become an infinite quantity. So 1 upon exponential of an infinite quantity, that will give you a number which is close to 0. So therefore for E less than EF at absolute 0, this is equal to 1. So that's why this value will correspond to a value of unity. So that's why we are having a straight line with value equal to unity for energy smaller than EF. Okay, so now let's try to figure out the behavior of this function. So in the second case, again at absolute 0, but now we are talking about energy for energy greater than EF. Okay, so this means when E is greater than EF, so then in that case E minus EF, it's going to be a positive number. Okay, so in this case exponential E minus EF upon kVt, that's approximately equal to, it's approaching infinity. So in that case the equation 1 predicts, okay, equation 1 will predict, equation 1 implies f of E, okay, that is equal to 1 over 1 plus infinity, and that will cause this function to approach to 0. So that's why for E greater than EF we are having 0 value for the probability distribution function. Okay, so this is a situation at absolute 0. So that's why this box like curve, it corresponds to absolute 0 temperature. Okay, so I'm going to label here this point as 1 by 2. Okay, Okay, now what happened when E is equal to EF? So at E is equal to EF, we are having a situation 0 divided by 0. Okay, when we put T is equal to 0, E minus EF, that will give you 0. A 0 by 0, that will give you a 0. Okay, so exponential 0. So that means at here that value corresponds to a value, the probability distribution function, it's a 1 by 2. So that means at E is equal to EF, the function it suddenly drop from value 1 to 1 by 2 and then to a 0 value above the energy E is equal to E greater than EF. Okay, now so that means at absolute 0, at T is equal to 0, I'm going to convey the message verbally now for the this diagram that I have drawn here. At T is equal to 0, all states with energy E smaller than EF are occupied. Okay, why? Because Fe, that is equal to non-zero value, unity. Okay, whereas for energy greater than EF at absolute 0, all states are empty. Why? Because F of E, that is equal to 0 here. Okay, now the next case, that is when temperature is not equal to 0. When temperature is not equal to 0, so that means temperature greater than 0 Kelvin. So in that case, so what will happen? So in this case, some of the electrons which are close to the Fermi level, so they will make a transition. Okay, and a situation like this will appear. Okay, so electrons from this region, okay, they will move and they will occupy the energy states above the Fermi level. Okay, so the states which will become empty below the Fermi energy, so same number of space will be occupied by the states above the Fermi energy. So these states now they will be occupied by the electron, whereas these states they will be empty. Okay, so these will be occupied. Okay, but this curve corresponds to T greater than 0 Kelvin. Okay, so therefore from this discussion and further, at E is equal to EF, okay, at E is equal to EF, what happens to the Fermi direct probability distribution function and T not equal to 0? So this is equal to 1 upon 1 plus exponential E minus EF, that is equal to 0 upon kVt, so that is equal to 1 by 2. So at E is equal to EF, this probability distribution function, it's having a value of 1 by 2. Okay, so this will cross through this value of Fe, that is equal to 1 by 2. Okay, so therefore here if you just take a look at the options, Fe is a step function. So at non-zero temperature, it's not a step function, so it is something like this. Okay, something like this. It's not a step function, it is a step function at absolute 0. Okay, so therefore A is not correct. F of EF has a value of 1 by 2. Yes, that's true, that just we discussed here. So B is the correct option here. Okay, for states with E less than EF are filled, completely filled. Okay, no, that's true only at absolute 0. So therefore at non-zero temperature, option C is wrong. And what about option D? Fe is large and tends to infinity as E decreases much below EF. No, that's not true. Okay, it's having a finite value. So let's take a look at the next problem. The temperature of the cavity is a fixed volume is doubled. Okay, so we are having a cavity. Okay, its temperature is doubled. So let's say initial temperature is T and the final temperature, which we are calling as T2, that is doubled from its initial value. So which of the following is true for black body radiation inside the cavity? Okay, so when we are doubling the temperature, okay, so let's see for black body radiation, for black body radiation inside the cavity, so following results are valid. Okay, so what are these results? Let's see. For instance, the energy density inside the cavity and pressure and the Helmholtz free energy. So A is the Helmholtz free energy. It is the Helmholtz free energy. So all these quantities, they are proportional to T power 4. So they vary with T power 4. Okay. So whereas a few other quantities, for instance, the heat capacity, the entropy, and the number density of the photons inside the cavity, they varies with T power 3. So when the temperature of the cavity is doubled, so that means these three quantities they will become 16 times. Okay, because 2 power 4, that will become a factor of 16, whereas these three quantities, they will become 8 times. Okay, so let's see which option is the correct one. So its energy and the number of photon become 8 times. Energy and number of photon, no, the number of photon becomes 8 times, but the energy becomes 16 times. So therefore A is not the correct option here. But what the option B? Its energy increases 8 times. No, energy is increasing 16 times because of the T power 4 dependence. So that is a factor of 2 power 4. So this is a factor of 16. Okay, so this is also not true. Okay, but what C? Its energy increases 16 times. Yes, energy is increasing 16 times, and number of photon increases 8 times. Yes, number of photon increases 8 times. It's a factor of 2 power 3 here, that is 8. So therefore C is the correct option here. And what about D? Its energy and number of photon increases 16 times. No, that's wrong. So therefore only option C is the correct one here. So let's take a look at the next problem. A sample of ideal gas with initial pressure P and volume V is taken through an isothermal expansion. Okay, so we are talking about the isothermal expansion. Isothermal expansion proceed during which the change in entropy is found to be delta S. So delta is the corresponding change in entropy during this process. The universal gas constant is R. Then the work done by the gas is given by. Okay, so for an isothermal process, we have, it should satisfy that dt that's equal to 0. Okay, because it's given to an ideal gas. So when dt is equal to 0, this implies for an ideal gas du that is equal to 0. Okay, so therefore if we apply the first law of thermodynamics, so from there we notice that dq is equal to dw, because du is equal to 0 in this case. Okay, so let's call this as equation 1. Okay, so that means from here we notice that work done is equal to the corresponding heat exchange involved. So what is q? That is equal to T delta S. Okay, so here we have made use of the result that delta S, that is equal to delta Q by T. Okay, which is basically the second mathematical definition of the second law of thermodynamics. Okay, because we are talking about an ideal gas, so T for an ideal gas, we can, for which this equation holds to PV, that is equal to nRT. So from here I can write T is equal to PV upon nR. Okay, so that means PV upon nR and then delta S. Okay, so therefore PV upon nR delta S. Therefore we see that option A matches with our result. So option A is correct here. So let's continue with the next problem. So hydrogen molecule of mass m are in thermal equilibrium at temperature T. Okay, assuming classical distribution of the velocity, the most probable speed at room temperature is given by. Okay, so in 3 dimension we know that in 3D we assume the isotropic velocity space. Isotropic velocity space. Why? Because of random motion of gas molecule. Okay, so the fraction of molecule, that is dn by n. Okay, it's given as with which are moving with velocity v at a certain temperature T. So this is denoted as dn by n, that is the function fv. Okay, that is equal to 4 pi m upon 2 pi kVt. This is basically the Maxwell-Boltzmann velocity distribution in 3 dimension. Okay, power 3 by 2 and then v square exponential minus mb square upon 2 kVt. Okay. So now, because we are talking about the most probable speed. Okay, so for obtaining the most probable speed, so what we are going to do is we are going to maximize this function. Okay, maximize it with respect to the variable which is velocity here. So that means while maximizing, we will notice that dfv divided by dv, so that is equal to 0. And if you take its differential of this function, so let me call this as equation 1, which is the Maxwell-Boltzmann velocity distribution. Okay, so here by taking its differential with respect to b, so I'm keeping all the constant terms outside. So what are those? This is equal to 4 pi m upon 2 pi kVt and its power 3 by 2, and then differential of these two terms with respect to velocity. So okay, so I'm taking the differential of v square, which will be 2b multiplied by exponential minus mb square upon 2 kVt plus now the b square as constant and differential of exponential term as exponential minus mb square upon 2 kVt, and then the differential of the exponent with respect to velocity, so minus m upon 2 kVt and then differential of v square, that will give you 2b, and this should be equal to 0. Okay, so that means what I can do is we will take the terms which are common in both expression inside the bracket, so we will take them outside. So that means 4 pi m upon 2 pi kVt power 3 by 2. Okay, so multiply by 2b, it's common inside the two expression inside the bracket. So and also the exponential factor we can take it outside, exponential minus mb square upon 2 kVt and into 1 minus mb square upon 2 kVt, and that should be equal to 0. So now this cannot be equal to 0 because b is equal to 0 has no meaning, so this cannot be equal to 0. So only this term could be equal to 0, and when we equate this to be equal to 0, so b here, we call this b as the most probable speed or velocity, you can say. So this after equating this expression inside the bracket to be equal to 0, we obtain the expression for the most probable speed, so that comes out to be equal to 2 kVt upon m under root. Okay, so that's the expression for the most probable speed. So that means that is equal to 2 kt by m, 2 kt under root, so it should be basically 2 kVt upon m. Okay, so therefore C is going to be the correct option here. So let's continue with next problem. The statement is the energy density of states of an electron in a one-dimensional potential well of infinitely high volts is given by, where symbol has the usual meaning. Okay, so now here we are going to make use of the standard results that you might have learned in your classes. Okay, so for the particle which is confined in one-dimensional box, particle moving in 1D box. Okay, the energy eigenvalues are given by En is equal to n square h square upon 8ml square, where n is equal to 1, 2, 3 and so on. Okay, so let me call this as equation 1. Okay, so from here what I can do is n is equal to 2L upon H, okay, multiply by 2me power 1 by 2. Okay, so let me call this as equation 2. So here, as we noticed in equation 1, n is changing by 1 unit each time. Okay, so therefore the number of microstates, because n changes by 1 unit each time, so therefore number of microstates is given by omega E, that is equal to the value of n, that is equal to 2L upon H multiply by 2me power 1 by 2. Okay, or this can also be rewritten as omega E, that's the number of microstates. So this expression 3 can also be rewritten like this: L and root m upon pi h cut and root 2 e. Okay, so just by rearranging all these terms. Okay, so therefore the correct option is A here. So okay, so A is the correct option here. So let's take a look at the next problem. Okay, the statement is a system consists of three spin half particles. The Z component of whose spin is SZ1, SZ2 and SZ3. Okay, can take value of plus half and minus half respectively. Each spin can take either a plus half value or minus half value. The total spin of the system is given as by this expression here. Okay, the total number of possible microstates of this system is, okay, so let's call this as question 1, this as question 2 and this as question 3. Okay, because it's a common statement for all of these 3 questions. So let's continue with the solution for question 1. Solution 1. Okay, so because each spin can have 2 spin orientation. Okay, each spin can have 2 orientation, that is, what are these orientation? Either plus half or minus half. So okay, so that means the number of spin orientation for spin 1, that is equal to 2. Similarly, number of spin orientation for spin 2, there are again 2. Similarly, number of spin orientation for spin 3, there are again 2. Now the spin orientation of any one of the spin, that's completely independent from the spin orientation for the next spin. So therefore the total spin, the total microstates, you can say the total microstates of the configuration, total microstates is simply the product of these different possibilities. So that is equal to 2 power 3 and that is equal to 8. And these 8 microstates are shown below. Okay, so if we just take a look at the possible spin orientation, so all spins, they are aligned in the vertical direction and they may align in the downward direction. So these are 2 microstates and other are 2 pointing in the upward direction, 1 in the downward direction, and or 2 pointing in the downward direction, 1 pointing in the upward direction, completely opposite to the upper one. Okay, the next possibility could be 1 pointing upward, other 2 pointing downward, and this is completely opposite of this case. And the last one, up, down and up, down, up, down. So these are the 8 different microstates here. Okay, so therefore for question 1, the right option is D here. So D is correct for the question 1. Okay, so now let's come to the question 2 here. The total number of microstates with Sz equal to 1 by 2. Okay, so that means Sz is given by this expression, so we have to look for the microstates for which the net spin will have a value of 1 by 2. Okay, so if we just take a look at all of these 8 configuration here. Okay, so only 3 configuration will have as Sz is equal to 1 by 2. Let's see what are those 3 configurations. So now coming to solution for problem 2. Okay, so here because Sz it is given by this expression, so I'm showing the calculation for the first case. So the Sz value for the first case, Sz value for this case is equal to, this implies Sz is equal to Sz1 plus Sz2 plus Sz3. So Sz1 here it is 1 by 2, 1 by 2, 1 by 2 for all 3 spin. Okay, so that is equal to 3 by 2. So basically we are not interested in this configuration. We are only interested in the configuration where Sz turns out to be 1 by 2, and that will be obtained when 2 spins will be pointing in the upward direction and one of them will be pointing in the downward directions. Okay, for instance this one. So for this case let me evaluate the corresponding Sz value. This implies Sz will be 1 by 2 plus 1 by 2 minus 1 by 2, and that is equal to 1 by 2. Okay, so that means so now we have to look for the configuration where 2 spins they are pointing in the upward direction. So this is the one of the such configuration for which Sz is equal to 1 by 2. So okay, so this will also give you Sz is equal to 1 by 2 and 2 up and 1 down. So this is the third one. Okay, and for other 2 are pointing in the downward direction and 1 in the upward direction. Yes, so these are the only 3 configuration for which we are having Sz is equal to 2. So therefore for the second the answer is 3. Okay, and these configuration which I have circled with this brinjal color, so these are the corresponding microstates. Okay, now what about question number 3? Consider an ensemble of system where each microstate has equal probability the ensemble average of Sz is. Okay, so that means for an ensemble where each microstate has equal probability, the ensemble average for Sz will turn out to be 0 here, because each spin is having a possibility to point in any direction. So net average will be 0. So therefore B is the correct option here for the question number 3. Okay, so let's continue our discussion with the last question from GATE 2003 examination. The common statement for these 2 questions is a gas of n particle is enclosed in a volume V at a temperature T. Okay, the logarithmic of the partition function is given by this expression. So we are given the expression for the ln z where V is a constant with appropriate dimension. Okay, if P is the pressure of the gas, the equation of state is given by. Okay, so let's continue with problem 1. Solution for problem 1. Okay, so the Helmholtz free energy free energy is A, that is equal to minus kB T ln z. Okay, so ln z, because that's given to us, so ln z that is equal to minus kVt ln B minus Bn into kVt power 3 by 2. Okay, let's call this as equation 1. Okay, so the change in Helmholtz free energy from thermodynamics, we know that that's given by dA, that is equal to minus S dt minus P dV. Okay, let's call that as equation 2. Okay, so from here we can calculate the P, that is equal to minus dA upon dV by keeping T constant. Okay, so then by making use of equation 1 and evaluating the differential of A with respect to B, we obtain curly V of, and then kVt outside and inside we have ln b minus bn into kV ln b. Okay, we can directly write it in terms of logarithmic, plus ln kVt power 3/2. Okay, now so this gives us b, that is equal to, because it's a differential with respect to b, so we need to worry about only the first term, because the second term doesn't contain any volume, so its differential will become equal to 0. Okay, so that means p, that is equal to kVt as it is, and then differential of logarithmic b minus bn with respect to v, so that will give us divided by b minus bn, and then again differential of v, so that will mean 1. So this implies the p into b minus bn, that is equal to kBt. So that's the required equation of state for the first case. Okay, so that means option B is the correct one here. So option B matches with the result that we have obtained. Okay, now let's continue with the next question. Solution for question 2. Okay, so here the internal, we have to figure out the internal energy, because we know that, because A, that's a Helmholtz free energy, that is equal to U minus Ts. That's a basic definition of the Helmholtz free energy. So from here the internal energy comes out to be equal to U, that is equal to A plus Ts. Okay, so let me call this as so this is our equation 3, and let me call this as equation 4. Okay, so S okay, so from here, from equation 2, we can also evaluate S, that is equal to minus dA by dt. So S, that is equal to minus dA by dt at constant volume. Okay, so that means this is equal to minus curly T of minus kBt ln b minus bn plus 3/2 ln kVt. Okay, and that is equal to kb, and then ln minus will become plus kv ln b minus nb into kVt power 3/2 plus kVt into 3/2 kVt, and then again further derivative with respect to t, so that will give you only kb. Okay, so let's call this as equation 5. Okay, so 4 and 5, so that means what we are going to do is, we are going to substitute the value of a and s here in equation 4, so then we will obtain the corresponding value of u. Okay, so when you do that, so finally, so by simply substituting a value of a and s in equation 4, so we will obtain that u will turns out to be equal to, u will be equal to 3/2 kBt. So rest of the terms will cancel with each other. Okay, so u is equal to 3/2 kBt. So which one? Yes. So for n, yes, because we have to figure out the result for the n particle. So therefore, for n particles, let's call the total energy as u dash. So that is equal to n times u. So that is equal to 3/2 n kBt. So therefore option C is the correct option here.